Hello everyone, this is Aditya, and today we are going to cover Engineering Mathematics 2 Algebraic Structures. So let's start with the video, but before that please do like, share, subscribe my channel and please support this video so that it can reach to maximum number of people. And now let's start with the video. So before understanding algebraic structures, you all should know that what is meant by a binary operation or composition. Well, let me define it first of all, and then we will see what it is actually. So let A be a non-empty set. Okay, then a mapping or function. Suppose this is it from A cross A, the Cartesian product, to A, which is denoted by this is the operation A cross A to A. This is how you represent it, is said to be a binary operation, binary operation or composition. We will see in a couple of minutes that what it actually means, but for now let's just understand its definition, and there's something more to go. So suppose for any element A comma B which belongs to A cross A, then the image of it under the operation this is denoted by this symbol. Okay, so A and B are your free images, and when you are operating this operator, then the image is this, right? It is similar to like if I say you have to add two elements to pre images. So A, suppose A cross A to A. So suppose A comma B belong to A cross A, then it means that A operation B is equal to A plus B. So this is how the binary operation works, right? So we have assumed a non-empty set, then a mapping or function like it goes from A cross A to A, right? Okay. Or function from this to this is said to be a binary operation or composition, right? Because this also belongs to A. It means that A belongs to A, B belongs to A, and A operation B also belongs to A, right? So a binary operation is taking from A cross A to A, right? So that is why this is how we represent. Okay, understood? So now let's see what is algebraic structures, right? Okay, let me read this. So now let's see what is algebraic structure. Okay, algebraic structure, right? So a non-empty set A together with one or more operations which satisfy some fundamental properties which are called axioms. No need to worry about them, we will discuss it. In this case it's like closure axiom and associative axiom and many other things. We will discuss it. No need to worry about that. Okay, for now just see the definition. axiom is said to form an algebraic structure, right? And notice that the operation may or may not be binary. Operation may or may not be binary operation, right? Or composition. Okay, so this is how the things goes. Okay, now let's moving to groups, and of course don't worry about it, we will discuss it soon. And yeah, one more thing, in this lecture we will be sticking to the binary operations only. Okay, so now let's see. Hold on. Let me erase this. So now let's see what are groups. Groups. Okay, so basically it is suppose a non-empty set G is said to a group a group if with respect to this, and here it is a binary operation, right? If you know the meaning of if means if and only if. Means this is the only condition, right? Only conditions. The first one, closure property. What is it? Let's see. Okay, so suppose for any two elements any two elements hmm, a comma b belong to G, then a plus b, I mean a and then a binary operation b, right? This is the binary operation b should also belong to, then belongs to b, right? And this is of course the definition of the binary operation only. Binary operation definition. If you remember, I said that if A belongs to A and B belongs to A, then A operation B also belongs to A. Similar is the case over here. If A and B belongs to G, then it implies that A operation B also belongs to G, right? Understood? Okay. So now let's see the second property. It is called associative property, right? Property, right? So let's see. So if A, B, C belongs to G, then A operation B operation C is equal to A operation B operation C, right? Fine, is it correct? Okay. Let me erase this so that I can get more space to write the third property. Okay. So let me erase this stuff and yeah. Okay. So let's see the third property, existence existence of identity element or identity. Okay, so suppose there's a condition, there exists an element E belonging to G such that E operation A is equal to A operation E is equal to A, right? And of course A belongs to G, right? Of course it has to be, right? And what is the fourth property? Let's see that also. Okay. The fourth property, it states that existence of inverse element or inverse, right? So each element for each element A belonging to G, there exists, you know the meaning of this symbol? There exists, it means there exists uh, an element A dash which belongs to G such that A operation A dash is equal to A dash operation A is equal to E, which is the identity element. Okay, so I hope you understood this, and let me recap everything so that you can understand it better. Okay, so let's see, and of course we will see it using examples also, lots of examples, so no need to worry. So first is the closure property, which is simply A belongs to G, B belongs to G, implies A operation B also belongs to G. Yeah. And second, associative property, it states that A belongs to G, B belongs to G, C belongs to G. It implies that A plus B plus C is equal to A operation B operation C, not plus. Okay, correct. And what is the third one? It is the existence of identity element. So for any element, there exists E belonging to, I mean, there is a E belonging to G, which implies that A operation E is equal to E operation A is equal to A, right? For all A. And fourth, existence of inverse. It means that there exists A dash belonging to G such that A dash operation B A is equal to A operation A dash is equal to E, which is, sorry, I'm not well, so that is why I'm sorry, actually I'm not well, so that is why. Okay. Uh, where E is the identity element. Okay. So now let's erase all this, and now let's see some problems, and I mean some theorems, and then we will see certain problems, and then we will see what is an abelian group, and then we are going to look subgroups. Okay. So now let's start with that. Let me erase this stuff. So now let's see how we represent a group and what are some of the theorems. So notice that a group is represented by, so this is the binary operation and this is the representation of group, okay, or simply G. And why I'm saying that group has to be represented like this? Well, because when we defined the group, we said that it is a non-empty set G is said to form a group with respect to a binary operation. So we are considering the group with respect to a binary operation. That is why we are showing a binary operator over here. But of course, if it is well defined, then we don't need to show if it is obvious. Okay, that is why. Now let's see some theorems. Suppose theorem number one. Let me erase this because it is now of no use. Okay. So theorem one, what it states, a group G or like this contains only one identity element. Okay. So how do we prove it? Let's see. So let's assume that let's assume there exists sorry there exist there exists two identity elements, identity elements, Sorry, I'm not well. So E1 and E2 belong to G, right? Okay. So you know from the property, from the existence of the element, of the identity element, E1 and then this must be equal to E2, then this, it must be equal to E2, right? And we can also say E2, then this is equal to E1, then this is equal to E1, right? Isn't it true, right? This is from, suppose from the property of E1, and this is from the property of E2, right? Since E1 is acting as an identity element, which means that when an operation, a binary operation is applied, is used over here, so it should give E2 as output if E1 is the identity, and same is the case with E2. But notice that E1 binary operation, E2, they both are similar, they both are equal, right? They both are equal, which implies that these two implies that E1 is equal to E2, which implies that there exist only one identity element, right? Okay. So now let's see another property. Okay. So now let's see theorem number 2. It states that if we have a group this, then each element has only one inverse, right? Inverse. So how do we check it? Let's see. So suppose there exist two inverse, suppose A1 and A2. I mean, let there exist, let's assume there exist two inverse elements, two inverse A1 and A2 belonging to G for A belonging to G, right? Then it implies that A plus A1 should be equal to element, the identity element, and of course A1 this, okay, and A operation A2 is equal to E is equal to A2 operation A, since we proved that there exists only one identity element. And now what we are going to do, we know the associative law, associative property, A plus A1 plus A2, it can be written as A plus A1 operation A2, which is equal to, what is A operation A1 is equal to E. So it is E operation A2, which is equal to A2. A2, right? Okay. So now we have A operation A1 operation A2. It can be expressed as A1 A2, A operation A2 operation A1, which is equal to E operation A1, which is equal to A1. And since from the property of associativity, we can say that A1 will be equal to A2, right? Which implies there exists only one inverse element for an element, right? For a given element, okay? Right, rest you can write, okay? Now let's see another property or theorem. So for a given group, this, we have to prove that A operation B is A operation C. It holds. We have to prove that this is equal to B is equal to C. I mean, this implies that B is equal to C. Okay. This is left cancellation rule or property. And second one, This is equal to A plus B is equal to C. This is the right cancellation property. This you will do on your own. Do on your own, and this I will do. Okay. So first one solution or proof. So A and then this B is equal to A, this C. Okay. Now we are going to apply the identity, I mean the inverse element of A. What it will be? Suppose A inverse operation A, this is equal to A inverse operation A operation C. What is this? This is E, this is E. Applying both sides A inverse on left side. Okay. Okay. So E operation B is equal to E operation C, which implies B is equal to C, right? From the property of the identity element. Okay. And this is very simple. And of course, you will do the this part, and similarly you will do this part also. It is very easy, right? And now let's see if anything else is left. We will do it. Okay, let's see what is an abelian group. Okay, let me erase this, then we will see. So now let's see what is an abelian group and what are its properties. Let's see. So abelian group is also called commutative group. Okay, I hope my spelling is fine. I guess it's correct. If it is not, then please do correct it. Okay. Okay, so of course it is a group. Okay, which means it will follow closure property. It will follow associativity. It will follow identity element. It will have identity element. It will have inverse, right? Inverse, right? And these things make it a group. But what else we have to add is that if A comma B belongs to G, then A operation B should be equal to B operation A, and it is the commutative property. Commutative property. So it should hold commutative property also to be eligible to become abelian group, right? Okay. So now let's do some problems, okay, and then we'll go to subgroups. Okay. So this is a question that we are given the set of integers, that is called the set of integers, and the binary operation, this, where binary operation is defined by A operation B is equal to A plus B plus 1 for all. This represent for all A comma B belonging to the integers, right? So you can pause the video and try this question, and now I'm going to solve this problem. Okay. So in this, we have to check that whether it is a group or not, right? Okay. So let's see it. So Z and then the binary operation is that. So let's check for closure property right now. Closure property. Okay. Suppose A comma B belongs to Z, right? Then A operation B is equal to A plus B plus C. I mean A plus B plus 1, right? And notice that A belongs to Z, B belongs to Z, 1 belongs to Z, which means A plus B plus 1 also belongs to Z, right? Which means that property verified. Okay. Okay. Now, what is the second property? Associativity. Associative property. It states, suppose A comma B comma C belong to the integers, then A operation B operation C is equal to, let's see what is it, A operation, what is B operation C? It will be B plus C plus 1, B plus C plus 1, right? Is it correct? A operation B is equal to A plus B plus 1. You can say it like the X operation Y is equal to X plus Y plus 1. Put X is equal to B and Y is equal to Z, Y is equal to C. You get B operation C is equal to B plus C plus 1. And that is what is happening over here. And now you can consider it as suppose capital B. So A operation capital B must be equal to A plus capital B plus 1. And what is capital B? It is A plus B plus C plus 1 plus 1, which is equal to A plus B plus C plus 2. Are you understanding this? How I did this? It is very simple. I assumed that this stuff is called B, capital B, and then I applied the definition of the binary operation which is given in the question, and we got this, and I substitute back the value of capital B. Okay. So let's remember this. It is A plus B plus C plus 2, right? Okay. Now let's do it like this. A operation B operation C, it is equal to A plus B plus 1 operation C, right? Okay, now you can apply it over here also. Assume it as capital A. So capital A operation C is equal to A plus C plus 1, which is equal to A plus B plus 1 plus C plus 1, which is equal to A plus B plus C plus 2, which means that associative property is verified over here, since A operation B plus B operation C is equal to A operation B operation C, which implies that associative property is verified. Okay. And what is the third property? Existence of the identity elements. Let's see that also. Not elements, it is elements. Sorry, I made a mistake while speaking. Okay. So third is the existence of identity element. Okay. Forget the spelling right now, what I have written. Okay. So suppose we are given A, comma B belong to what is this side? Z. So we assume, let's assume there exists E belonging to, let's assume that there is an identity element E belonging to Z. Okay. So it implies that A operation E must be equal to E operation A must be equal to, let's apply this now. We get A plus E plus 1 must be equal to A, right? Since this is the definition, it must be equal to A. Now let's apply A plus E plus 1 is equal to A, which implies E is equal to -1. And we indeed got an identity element. So it means that existence of identity is also proved. Now we have to check for inverse. Let's see that also. Let's erase this for that purpose, and we will see further that what exactly is it. Okay. So existence of inverse element, inverse of an element, right? Of an element. Okay. So suppose A inverse belongs to Z. Suppose for all A belonging to Z, there exists A inverse belonging to Z such that, are you understanding what I have written? For all A belonging to Z, there exists an A inverse belonging to Z such that A operation A inverse is equal to A inverse operation A is equal to E, the identity element. So let's substitute. We get A plus A inverse plus 1 is equal to E. What is E? E is the -1. E is -1. So A inverse is equal to -2 minus A. And which implies A inverse belongs to Z, right? And here E belongs to Z from this, right? Which means that there exists inverse of all the elements in the given set, in the given group. Okay. And of course, if you want, you can check for abelian also, and it is also abelian. Why? Because a operation b is equal to a plus b plus 1, b operation a is b plus a plus 1, and they both are equal. So it is an abelian group actually. But since we were asked to prove that is it a group or not, so it is a group, and of course it is an abelian group also. Now let's see another question. Okay, let's erase this. So this is our second question, and in this we are given that prove that set of all real matrices, and this is the matrix such that a square plus b square is not equal to 0, form commutative group with respect to multiplication. You can try this one, and now I'm going to solve this. You can pause the video. So let's check for the closure property. Closure property. Suppose we represent this as set A, right? So A belongs to, suppose A belongs to group G, right? We have assumed, and B also belongs to G, right? For the timing, we are assuming G, okay? Then A operation B is equal to A multiplication B, right? Correct? Okay. So it means that it will be equal to A B negative B A into C D negative C, I mean negative D C, right? And when you evaluate this, what you will get? You will get A C minus B D, and you get A D plus B C minus B C plus minus A D and minus B D plus what is it? Minus plus AC, right? Okay, so we got this. What is the determinant of this? Let's see. Okay, but wait, it is AC minus BD. This is AD plus BC, A AD plus BC. This is AC minus BD, right? So it is of this form only. Notice that if we assume this as suppose arbitrary A dash and this as B dash, so this is negative B dash and this is A dash, just like this. And when you take the determinant, what you will get? AC minus BD whole square plus, I mean minus AD plus BC whole square, right? And of course there was a negative sign, so it will become plus. And when you solve this, you will get A square plus B square into C square plus D square, right? And notice that since A and B belong to G, which means that A square plus B square is not equal to 0, and C square plus D square is also not equal to 0, which means that their product also does not belong to 0, is not equal to 0, which is also not equal to 0. So it means that in this case also we are getting the same result, right? Since this is just the determinant of this quantity, right? A square plus B square, right? So it means that it is a closure property, which means that which implies A operation, I mean A operation B also belongs to G, right? Okay. So this is how you prove it. And the second property is the associative property. And you know, for every matrix there exists associative property, right? This is the basic law which you know. And you know that under multiplication matrices are associative. Okay, that is the basic thing which you know. Okay. And the second and of course you have to prove that also using the elements A B C D and E F. You take the elements, you show the product that they both are equal. You have to prove that. Okay, I'm not doing that, that is your homework. Okay. And the third thing, the existence of identity element, of course, I 1001, right? It is the identity element. So when you multiply by it, you get the same matrix. And for the existence of inverse, of course, the matrix should be non-singular, which means that its determinant should not be equal to 0, and which is true in this case. So it means inverse exists, right? And for the fifth case, for proving it to be abelian group, and from those four we have proved that it is actually a group, and from the fifth one we have to prove that AB is equal to BA, and that is your homework. It is just simple multiplication which you can do. Okay, so let's move into the next question. Okay, and that is also your homework which I'm giving. Okay. You can try it. Okay. So this is the question that prove that set of all complex number a plus ib where I is equal to the square root of -1 and a comma b belong to the real numbers and a square plus b square, that is the, suppose if I represent it as z, then mod of z square is equal to a square plus b square is equal to 1. We're given this, form abelian group with respect to multiplication. So it is similar to the case of matrices, but now we have the imaginary numbers and it is easy. You can do it, okay? For closure, you will do a plus ib into c plus id and you will check for the mod of that value, what you of that complex number, right? And for associativity also you have to prove that you take first two group and multiply it with the third one, and then you leave the first one and then you multiply second, third, then multiply it by that. Okay, so from that also you can check. And for the third one, existence of identity element, of course you can do like that. Okay, you know, a plus e, I mean a operation b must be equal to a, which means a plus ib multiplied by e must be equal to a plus ib, so e is equal to 1, right? You got this. Okay. And similarly, a plus ib into a into a inverse, or suppose x inverse, else it will become confusing, is equal to 1. So you can solve x inverse is equal to 1 upon a plus ib, which is equal to a minus ib by a square plus b square, right? Is it correct? Okay. So this is how, and it is actually equal to a minus ib, right? So in this case, inverse is a minus ib, right? Okay. And when you multiply them, of course, you will get a square plus b square, which is equal to 1, right? From the given definition. Okay. So this is how you can check it. I'm not solving the completely. It is your homework to try it. I explained the problem. Okay. So now let's see another problem. This is a very simple question. The set Z forms commutative group with respect to addition. Justify. So you have to just assume elements a belong to z, b belong to z, c belong to z, and then just a plus b belong to z. It is true. Then for associativity, a plus b plus c is equal to a plus b plus c. This is also true since it is addition. Existence of element a plus e is equal to a, which means e is equal to 0. So e is the identity element, and a plus a inverse is equal to 0, identity element. So a inverse is equal to negative a, so where there exists inverse also. And for abelian you can try using a plus b is equal to b plus a, so it is commutative also, so it is abelian. Rest it is your homework to do it correctly, properly, in a proper manner. Okay, I told the method. So now let's see that what is meant by a subgroup. Let's see, just a minute, let me erase this. So what is a subgroup? Let's see. Suppose you have a group G like this, okay, and H be a non empty subset of G. Now if H is also a group, then it's called the subgroup of G, right? Okay, so suppose you have a set H, which is a subset of the bigger set G, which is said to be a group. Then if H is also a group, then it is called a subgroup of G, right? So basically, if G is a given group, and of course a group is a set also, then if there exists a H which is a non-empty subset of G, such that H, and here the binary operation is this, is also a group. If that is also a group, then we say that H is the subgroup of G. Okay, this is the basic thing which I need to tell. And there is a theorem which is used to check whether it is a subset or not. I mean subgroup or not. We are going to discuss that. We will see a problem and then we'll end this lecture. And yeah, we will do more problems and we will study about Zn function and all in the practice session, because that will be more helpful, right? Right now I gave the basic idea so that you can do everything, right? Okay, so now let's see the theorem. We won't prove this one. Okay, if you want you can try as a homework. Okay, so let this be your group, be a group, a non-empty subset H of G forms a subgroup forms a subgroup forms a subgroup of if and only if, first, for all A comma B belonging to H, A operation B must belong to H, right? This is the first condition. And second, for all A belonging to H, there exists A inverse belonging to H. Means there exists inverse, and this is a definition of the binary operation or the closure property, right? And this is your existence of inverse, right? So let's see one problem and then we will end this lecture. Okay. So let's see the question. It states that consider the group Z, and here the binary operation is the plus, and the set 2Z. What does 2Z mean? For example, it's a set of integers. It's -2, -1, 0, 1, 2, till infinity, till infinity. Then 2Z is defined as twice the elements of Z, which means -4, -2, 0, 2, 4, and so on and so forth. Which means that set of all even integers, right? So this is the definition of 2Z, and now which means that it is the subset of the original set Z. Okay, defined by 2Z is equal to this quantity. Examine whether 2Z form a subgroup with respect to plus or not. Okay, so the first one, we have to prove that H itself is a group or not. So we will see it using the closure property. Closure property that suppose A belongs to H and B belongs to H, and of course we are given that Z is a group, so we don't need to prove that. Okay, which implies A operation B is equal to A plus B, right? Now the question is that whether it belongs to H or not. Well, you know that A belongs to H, and what is H? H is 2Z over here, and B belongs to 2Z again, which means A is of the form 2x and B is of the form 2y, which means 2x plus 2y, which is equal to 2 times x plus y, and which itself is an even integer, which means that, which implies A plus B is itself belonging to H, right? Or 2Z. Here H represents 2Z, or you can represent simply 2Z also. That is also fine. Okay. Now let's see the second property, the associative property. It states this A, this, and then this. Of course, it is true, since A plus B plus C is indeed equal to this quantity. You add it in any way, it is still the same. Okay. Now let's see existence of identity and all. We will see that, and let's see. Let me raise this also. Yeah. The third one, existence of identity element. So if A belongs to H, then A operation E must be equal to A, right? If E belongs to A, correct? I mean belong to H, sorry, it implies that A plus E must be equal to A, which means E is equal to 0, which means E belongs to H. Why? Since E is equal to 0 and 0 is an even number, right? If you understand this. Okay. Now fourth one, existence of identity element, I mean existence of inverse for any element. Any element. Okay. So A, suppose A inverse belongs to H, and of course A belongs to H and E belongs to H. We have found E is equal to this quantity. So we have A operation A inverse is equal to E, which means A plus A inverse is equal to 0, which means A inverse is equal to A negative, right? And since it is integer, A is an even number, so negative A is itself an integer only, even integer, right? Which means it is a group. And now we have to check whether it is abelian or not, abelian group. To check for abelian group, we have to check whether it is commutative or not. Well, we don't need to check for abelian actually, but still, if you check, it will be A plus B and B plus A, and of course, it is commutative, so it is abelian group also, right? And this is how you check. It is very simple. You prove that it is a group, and of course, you could have used the theorem also. That is also fine. But this is a more better way to solve these kind of problems, right? So I hope that you have enjoyed this video and understood all the concepts of groups and subgroups. And of course, this is not the end, and we will see some better problems in the practice session. In that, we will learn many other types of groups like the Zn group and all. And for now, bye bye, take care, and please do like and subscribe my channel, and please support this video. Bye bye, take care.